Hi, I'm going to walk through a notebook on PID controllers. If you're looking for a simple control mechanism that has a feedback loop, this is what you'll need. PID stands for Proportional Integral Derivative. To better understand what is happening, let's take a look at an implementation. So here we work out the error. Then we work out the integral, which is the deviance of the current signal from the target signal. And then finally we have the derivative, which is the change in the error, and that is used with the gain factor to create our signal. So let's graph those composite parts. So here the yellow is the control signal, the red is the proportional part, and then the blue is the integral, and the green is the derivative. So my target value is 30 and my current value is 0. So if we think about that, when we start out, the error is highly positive, but the PID controller actually makes the value overshoot the target. And then with the integral, as the deviance between the target value and the current value decreases, so the line gets closer and closer to the 0 value. And the derivative is the gradient of the error. So when we start out, the gradient will be positive. So then when we overshoot, the derivative inflects, and then again it converges on 0. So to better understand the proportional, integral and derivative aspects of the controller, we can play about with the gain values. So with these values, the control signal will mostly be made up of the proportional part. And this is what it looks like as a result. So it takes a long time to converge on to 0. So now let's change the gain values so that the PID controller is mostly using the integral, and as we see, it's very turbulent. We end up overshooting and then undershooting, overshooting and undershooting until eventually converging. So now if we look at what happens when we mostly use the derivative part of the signal, we get a similar unstable behavior, which gives us an idea of the sort of gain factors to use. So we mostly want to use the proportional gain signal so that we don't have the ripples and the turbulence. And so it becomes a case of tweaking the gain values until you get the behavior of the PID controller that you are looking for. I'm quite happy with this behavior. We quite quickly converge on the target, and changes in the signal aren't too abrupt. Here's a different visualization of the same control signal. So the PID controller overcompensates, and then the signal comes down to the target value. So any small project that you have that needs a control system and has a feedback loop, PID controllers are a great option.